So we've talked a lot about binary search trees and how to insert into them and how to delete from them. And last class we saw that usually they're pretty balanced. In fact, usually they're very balanced. So probabilistically, if you have average input, then you have a nice logarithmic height tree. So that's good. And in your problem set, you'll see some ways to sort of force that, even if the input is not randomly distributed. But today we're going to look at some structures, some data structures that avoid randomization and in the worst case have logarithmic height. So that's our goal. So we want some binary search tree data structure hyphenation right, with guaranteed logarithmic height. And this is easy from the beginning, but the hard part is we want to support updates. We want to support insertions and deletions. And so let's just call that the dynamic set operations. So that's our goal. And there are many examples of balanced search tree structures. And in this course, I think we will cover two, I think. Definitely one today and one in recitation on Friday. I think the first one was AVL trees. And on recitation, you'll see B trees and something called 2-3 trees. And today we're going to talk about red-black trees. Okay, so the rest of the lecture will be about red-black trees. Red-black trees are very slick, you could say. Okay, it's going to be a very nice data structure all the time, logarithmic height, supporting all the operations you could want. The details in the end get a little bit complicated. There are a few cases you have to deal with, but it should go relatively smoothly. I think I will go relatively quickly because there are a few details that we need to cover. So the first thing you want to know about red-black trees is why are they called red-black? Right? And the reason is there are two colors, red and black. So each node stores a color in a 1-bit field. Okay, and the first property about these colors is that every node is either red or black. Okay, so that's where the name comes from. And now the red-black properties are the key things you want to know about red-black trees. They're the invariants. Okay, this data structure is going to go through lots of changes when you insert and delete nodes. And there'll be, I think, 5 invariants that will give us balance. As long as we can maintain these invariants, we'll get balance and nice logarithmic height. Okay, some easy properties is that the root of the tree is always black, okay, at the end of every operation. Another property is that the leaves are black. And in this structure, we're going to it's very convenient to assume that every node has degree 2 or degree 0. So either 2 children or no children. So we'll actually treat the nil pointers as pointers to a special node called nil. Okay, and those nodes are all black. Okay, that'll just be convenient. And we'll see an example in a moment, so this won't be so bizarre. The next important property is that if a node is red, then its parent is black. Okay, this is important. It's saying we don't want too many red nodes. We're not allowed to have 2 red nodes in a row vertically. Okay? You can have lots of black nodes in a row. That's fine. Black nodes will be good for us. This is somehow what will give us balance. But we need one more property. Let me get the wording right. So suppose we take any node x. Then if you look at all simple paths from x to a leaf, they all have the same length in terms of black height. So all of these paths have the same number of black nodes. Okay, so we're not counting the red nodes in these paths. And we know that there aren't too many red nodes, and so this will do us well. That's the idea. But this, OK, don't want to jump ahead of myself. This is really, in some sense, saying that it's perfectly balanced if you just look at the black nodes. Okay, we'll see that more formally in a moment. And definition, the black height of a node x is essentially the length of these paths. Okay? All of these paths have the same number of black nodes, so just count that number of black nodes, excluding x. That's the black height. Okay, because they're all the same, this is well defined. Okay, except you don't count the node x. That'll just make the arithmetic work out. So let's look at an example. I mean, this is lots of math. But once we draw a picture, it'll be fairly clear what it means. So here's an example of a red-black tree. And I considered using red chalk, but how many people have red pens? One person, right? So to save you from switching around with colors and so on, I will use a little b to denote a black node and a little r to denote a red node. I need some more colors. Okay, all of these little nodes with no numbers in them, those are the nils. Okay, so this is sort of the real tree, but then wherever we have a nil pointer, we're adding on this little extra black node. Okay, so that we don't have to worry about boundary cases. 3 should be black. Thank you. Trying to keep consistent with the online notes. Rest are OK. OK. So the height of this tree is 4, if you count it right, counting the number of edges. And, well, we should check that it's a red-black tree. So let's check all the properties. The first thing is that every node is red or black. Okay, that's clear. I haven't labeled these black, but all of these are black. Second property is that the root is black. Good. These are easy. The leaves are all black. That was sort of the definition. The fourth property becomes a little more interesting. If a node is red, its parent is black. Okay, there are a few red nodes. There's one here. Its parent is black. One here. They have a black parent. And there are no red nodes adjacent vertically. Okay, and then the fifth property, if we look at any node, so maybe I should first show you what the black height, how that's behaving. So, for example, all of these nodes at the bottom, they have black height, which I'll abbreviate BH, of 0, if you count it right, because you exclude the node X. So the black height of a node of a leaf is 0. The black height of this node is it's too easy. Raise your hands. Yeah. 1. Right. Because this node is black. Good. Black height of this node, running out of space, but is, you have to get, I mean, it's a little tricky. You have to get the boundary cases right. 1, right. So we don't count this node even though it's black. The black height of this one is now 2 because of this black node. And the black height here is 3? 2. Good. OK, you're being careful, despite it being early in the morning. OK, so those are, he's cheating. Hey, you're not allowed to look at the notes. OK. And it's some effort to verify this property. But you can check from any node, if you follow along a path to a leaf, the number of black nodes that you visit is the same. So there's always one here. And if I go this way, I reach this black node, no matter which leaf I go to. This way, I reach one black node, no matter which way I go. And this way, I reach one black node. OK, so that's good. This is a red-black tree. And the first thing we want to know about red-black trees is that they're always balanced. So these properties will be enough for maintaining balance. So the theorem is that red-black trees always have logarithmic height. More precisely, a red-black tree with, let's say, n keys has height, let's call it h, at most twice log of n plus 1. Okay, you can check it here. The number of nodes is 7. The number of keys is 7. Okay, so we're not counting the leaves. Log of 8 is 3, right? Times 2 is 6. So this has height 4, which is smaller than 6. Good. Easy enough. And this proof will, I think in particular, show you what's going on with red-black trees. These definitions may seem a little artificial, but once you see what's going on in this proof, you'll understand what's really going on, I would say. The book is a different proof using induction. You should read that proof because it's a good example of induction. Say you should read it thoroughly. Okay, don't just read it. But I want to give a more intuitive proof, which really gives you the picture of red-black trees and their definition and why they're balanced and so on. So here's the idea. I don't have too many red nodes next to each other. So what happens if I just look at the black nodes? How could I throw away the red nodes? Any ideas how I could throw away the red nodes? How could I change the tree and just get the black nodes? And I can't just remove them because then I have lots of little trees hanging around. So what should I do? Yeah?
Recolor every red node with black node.
I could recolor every red node with black node, but that's not going to help me too much because then I really have the same tree. So I'd like to make my tree smaller and just care about the black nodes. Because then if I color the red nodes black, then I'm sort of caring about them. The tree looks like it did before. I want to be able to forget about color and have a nice looking tree in the end. It's a tricky one. How many people have taken something in graph theory? I mean, I guess 604.2 covers some kind of graph theory. Have you talked about contracting edges? Contracting two nodes? One nod. Anyone else? Okay, so some people have seen contractions. That's what we're going to do. A contraction is just sort of merging two nodes. So I'm going to merge every red node into its parent. And the parent is black by property 4. Okay, so this is within the proof, but this will be useful for understanding what's going on. So let's do that for this tree. I want to merge this red node, for example, into this black node. Okay. Why don't I use another color? I just happen to have red around. I'm going to do that merge. Here I have some red nodes. I'm going to merge both of those red nodes into the parent black node. Okay, and similarly over here. And what do I get? I'm going to want these properties still. Probably. So remember, the height of this tree is 4. So what I get when I do these merges, if I merge these two nodes, I can draw that as a box with both 7 and 18, say. To the left of that, there's 3, just like there was before. Okay. Eight and 10 and 11 are all going to fall into one node. And also 22 and 26 go in the same node. Okay, that's sort of what I have in the end. Okay, just by merging. You can think of there's a pointer here, a child pointer, which is everything that fits between 7 and 18. Okay, that was this subtree here. Okay, this tree looks really nice, right? That one didn't look so balanced, but this one looks pretty darn balanced, doesn't it? So that's what we want to argue. Okay. I'm afraid I have to erase some definitions. So if we do this merge, we get another tree. And the tree has two important properties, and I would like you to tell me what they are. In particular, the number of children of a node. How many children? I mean, I now have nodes with more than 2 children, but how many could I have? This requires some thinking about how many red nodes can be involved here. Okay, I'm merging red nodes, but I know that I never merge a red node into a red node. Can't have too many merges at once. you have an idea? Maximum of 3 in each merge. Yeah, whenever I merge, before I had 2 from each node, but they were adjacent, so there's only 3 outgoing edges. And then how many merges could I have? So at most 2, right? Like here. Okay, I can have 2 red nodes merge into a black node, but no more. So the maximum number of children I can have is 4. Right. Very good. In fact, it's always, it could be 0 for a leaf, or it's 2, or it's 3, or it's 4. Okay, depending on how many we merge. So that's cool. We have bounded degrees still. That will be important for this proof, to say how small the height is getting. The other thing, what other property do we see about this tree? Why does it look so good? Why does it feel balanced if you forget about how many children there are from each node? Yeah?
Because its height is the black height of the root.
The height is the black height of the root. Very good. I mean, I was just thinking all the leaves have the same height, have the same depth. But in particular, that depth is exactly the black height of the root. Yeah. Okay, if you forget about some of the nodes having more than 2 children, this is just like a perfectly balanced tree. Okay, that's cool, because we very quickly find out what the height is. This is called a 2-3-4 tree. Okay, and you will learn more about these kinds of trees in recitation on Friday. But I wanted to mention this connection because it's very easy from this to prove the theorem. Okay, we want to analyze the height of this tree. The height of this tree is, it's another easy one. Should answer the easy questions, right? Anybody? Yeah, 2. Okay. 2 is half of 4. Okay, big observation. That will actually be true in general, that the height here is at least half the height of that. So let's call this height h prime. Okay. Then I want to argue that h prime is always at least h over 2. Why? Exactly. And any path from the root to the leaf, only half the nodes can be read. Yeah. So if we say take some root to leaf path, at most half the nodes are read. Cool. This is important because the height of this tree is rather easy to understand, right? You should be able to write down an equation about that. I think I won't fit it here. So if we want to analyze the height of this tree, maybe the easiest thing is to count the number of leaves. So can anyone give me, let's say, a lower bound on the number of leaves in this smaller tree? In terms of its height. So we want to know its height. H squared. Well, here it's, yeah, right, it's h squared, because each time we're, wait, h squared. That's not quite the right way around. It's sort of upside down, yeah.
Maybe 4 to the h of everything.
4 to the h, yeah, it's at most 4 to the h, that's right. H prime, of course, because each node has at most 4 children, like here. So the number of leaves is definitely at most 4 to the h. We actually want a lower bound on the number of leaves. So how small could each node be? Yeah. 2 to the h. Yeah. 2 to the h prime. Good. So that gives us, because this is a lower bound on the number of leaves, we get an upper bound on the height. So the height of the tree is at most, is this the way I want to go? I guess first I should ask you, we also know exactly how many leaves there are, and this is a little bit trickier. Okay, what do we know? We know that the tree has n keys. Let's see, am I messing around? Okay, the important thing, I'm saying the number of leaves in this tree, but in fact the number of leaves is the same in both trees, right? I never merge leaves because they're always black. Okay, that's important. So I can just say the number of leaves and not say which tree I'm talking about. How many leaves are there in this tree in terms of n? There's actually a very nice formula for this. It's not quite n, but it's about as simple as they come after that. Think back to 6042, some discrete math. You have a binary tree, every node has degree 2. So the number of leaves is n plus 1. Yeah. So that's cool. We also know the number of leaves is equal to n plus 1. Okay, just because every node is branching 2 ways in that tree. Okay, so now we get a connection. This is h prime. The superscript, it looks dangerously like n. So let me rewrite it. So now we have a connection between these two things. So these two mean that n plus 1 is at least 2 to the h prime. Cool. Now we want to know what h prime is. This should give us an upper bound on h prime, which is I'm going to play the Charles trick. So someone in that back corner, how can we bound h prime in terms of n using what we know? Any ideas? Just need to manipulate what we have already. Log of n plus 1, right. Good. Okay, that's h prime. But what we really wanted to know about was h, the height of the original tree. Okay, but we know a connection between h and h prime, which is this. Okay, so if you flip that around, it's saying that h is at most 2 times h prime. So h is at most twice this. Okay, and we're done. Any questions about that proof? So this should give you a picture of what's going on with red-black trees. If I contract the red nodes into the black nodes, I get something called a 2-3-4 tree, which you'll play with more on Friday. And it's nice because it's perfectly balanced. All the leaves are at the same level. Okay? The node degrees go up a little bit, but not by too much. They almost double. Okay, now, so that's why red-black trees are always balanced. If we can get these properties. The hard part is to maintain those properties. So someone comes along and takes our favorite red-black tree there and inserts a node. What do we do? Okay, we're going to have to make some changes and recolor things and rebalance the tree so that it still has the 5 red-black properties. Before I go there, I should talk about queries. So this is a corollary. There are a bunch of queries we might want to perform on dynamic sets. I believe we've seen all of them already from a couple problem sets ago. Search is the most important, but then there's min and max and successor and predecessor. Right? Well, if we have a nice balanced tree with logarithmic height, we know they run in logarithmic time. Okay, you just walk down the tree. Or in successors and predecessors, you walk up and down. But this is all straightforward stuff. Okay, so queries are fast. The hard part is updates. How do we do insertions and deletions and maintain all of these nice properties? And this is where the structure becomes somewhat intricate, but also very slick. Okay, we want to know how to do insertions and deletions. And they're going to have to make lots of changes to the trees. So what sort of things could we do? And the first thing I want to do is just like binary search tree insertion and deletion. Okay, we know we can walk down the tree and stick our node there for inserting. I'll talk mostly about insertion. So I'm going to walk down the tree, insert the node. That's easy. Then the hard part is we have to maintain the properties. So we can do BST sort of thing. I think it's called tree insert and tree delete. What else could we do? So there are many answers to this. Let's see. We're going to need at least a couple of different things we could do with red-black trees. And so we stick on the node. First thing we should do with that node is color it. Yeah. So we're going to have to assign colors. Okay, because we add a node, it's got to have a color. It's going to be a red-black tree. Well, then we might not satisfy the red-black properties. So what else could we do to make them satisfied? Any ideas? This is like algorithm design. This is tricky. Alternatively, it's whoever read the textbook ahead of time, or whoever's sitting in front of the lecture notes. Oh, you know. No, I know you. You wrote the textbook. You co-wrote the textbook. That's even easier. What else can we do? You have some ideas? Restructure the tree. Right. We'd like to restructure the tree so that the black heights don't change, because they have to be equal at every node. So that's a good, I'll just say restructure. The sort of restructuring we might do is moving pointers around. Okay, we can make one node higher than it was before. As long as its black height stays the same, that'll be pretty good. And the other thing we might do, this is sort of obvious because we already said assign colors, is you might want to recolor the nodes. Right? We can change the colors. They're not fixed. And that'll be useful as well. In fact, most of the time we'll spend is in recoloring the nodes in some sense. Okay, so that's sort of an outline of what we're going to do. And now it's a matter of implementing it so it all works. And I think the easiest thing to do is an example. But not quite. So I want to tell you what kind of restructurings you can do, first of all. We're going to use something, and this is harder to guess. So we're going to use a particular kind of restructuring, sort of the simplest thing you could do. It's called a rotation. And we want to draw sort of an abstract picture of the tree. And I'm not worrying about colors at this point. Okay, so suppose at some point, my tree looks like this. I have this node as A is a child of B. They have these subtrees hanging off of them. There's some rest of the tree above us. We just want to focus on this level. And I'll label these subtrees alpha, beta, gamma. And we can convert that into a tree where A is above B. And in particular, we'll do this with the subtrees. Okay, and this rotation, this is called a right rotation. Of A. It preserves all the properties we sort of want. Okay, so what do we want to preserve? I mean, what's good about this rotation? I mean, we have a BST tree. What is the property of a binary search tree? Yeah. Right. The values on the left of the node are less than that node. The values on the right of the node are bigger than that node. So here, everything in alpha is smaller than A. And that's still in the right place. If we know that everything in alpha is smaller than A, we still have the property on this edge. Okay, and you can check that works everywhere. So we preserve the binary search tree property. In other words, we talked about traversals, right? So this is also the same as preserving the in-order traversal order. Okay, because in a binary search tree, if you do an in-order traversal, you should get the elements in sorted order. And you can check you'll get them in exactly the same order. Okay, so that's equivalent. So that's good. We could also go in the other direction. It's called a left rotate. It's more or less arbitrary at this point. If we're not worrying about colors, then we can just do this. If we just want to maintain that it's a binary search tree, we can do either of these operations. How long does a rotation take? How much time? Order 1, yeah. This takes constant time because we just have to change a few pointers. Okay, the left pointer of A doesn't change. The right pointer of A goes to B now. The parent pointer of B goes to A. Left pointer of B changed. That's it. Okay, so that's easy. So rotations are fast. It's just a question of how many are we going to need to do in order to fix up our tree. Okay, so let me give you the outline of the insertion algorithm. The idea is that we're going to insert our node. Suppose we want to insert X. We're going to insert it into the tree just like a binary search tree. And we're going to give it a particular color. Which color should we give it? It's always going to be the same. Okay, you mentioned something about preserving black height. So if we made it black, that would screw things up, right? So we should color it red. Yeah. Good. We had a 50% chance of being right, so that's good. All right. Because that's going to preserve black height. So that's good. I mean, I've erased the invariants, but you should have them all written down. That will preserve pretty much all the invariants, because the black heights aren't changing for any node. Okay, the only trouble is we might have a red node next to a red node now. It's the only thing that could go wrong. Okay. So when would we now have a red node above a red node? I've only inserted one node. I've only made one change. What's the problem situation with X? See, when we add at x, it has a couple of children, which are these nil leaves. But they're black, so that's OK. So what could go wrong? Yeah? Right, the parent could be red. If the parent's red, then we have a problem. We violate property 4. OK, so we've got to fix it. This is called a violation of our invariance. So we'll move that violation up. Entirely by recoloring. Okay, we're not going to do any rotations at this step until we get up to a point where we can do rotations and fix it. Okay, so this is a little mysterious at this point. Until we're high enough and the violation can be fixed just by some rotations. It should not be obvious yet when this happens, but we'll see. We'll see it soon enough. So the idea will be, well, actually, once we get high enough, we'll do some recolorings to move the violation up. Then eventually, we only need a constant number of rotations. 2 rotations, and we'll be done. So that's good. Let's look at an example. Oh, dear. The return of the stuck chalkboard. OK. So let's look at our tree here again. Let's suppose that I want to insert a particular number, 15. Okay, if I want to insert 15, I just walk down the tree. It's bigger than 7, smaller than 18, bigger, bigger. It goes here. Okay, so I'll redraw it because you'll have to copy it in your notes anyway. So 18 will go here. Sorry, 15. And all the other nodes are the same as before. And they're colored the same, black, black, red, black, black, red, red, red. This one will be colored red, because that's what we said, the initial coloring. So this is after the first step of insertion. And we have a bunch of nil nodes hanging off. This red refers to this node. OK, and we have a violation because the parent of 15 is red. And step property 4 says that your parent should, if you're red, your parent should be black. OK, so we want to fix that. The way we will fix that is fairly easy. We're going to concentrate on these nodes. OK, there's a black node up here and 2 red nodes. OK, we'd like to make this node black. So does anyone see how to do a local fix there? What could we do? Any ideas? So we can do this purely by recoloring and fix this problem. We have a problem along this edge. I'll highlight it. Yeah. Make both 8 and 11 black. Yeah, that's looking good because then these 2 nodes have the same black height. Right, so from here, if you count the number of black nodes to get to a leaf, it'll be the same. There's a problem with that. Anyone see the problem? If we just make these 2 nodes black and keep everything the same, everything else the same. Yeah?
Doesn't that change the black height from 18?
Right. From 18, the black height changes, because now over here I only visit one black node, and going down here I visit two black nodes if I make these two black. Okay, so that doesn't quite work. You have a fix? Yeah, sure. I don't know. Anyone? Yeah. Make 10 red. Yeah. So we're going to invert the colors of all of these nodes. Make this red, these two black. Black heights will all stay the same. So that's the essential idea in this part of the insertion. Okay, so this is just a recolor. So I need to copy the tree again. Good. And we're going to flip these so that this is red, these two are black. Okay, and you can check the black height from every node is well defined. In other words, from every node, you go down all the same paths, all the different paths to a leaf, the number of black nodes you visit is the same. So are we done? We fixed this edge. It's now, the parent of 15 is now black. Okay, if I'm asking, we're not done. So 10 and, right. So now this edge is the problem. So all we've done is move the violation up, but that's progress. So these two are red, as you said. Sounds like the beginning of a nursery rhyme. So we want to fix these two. And we'd like to apply the same trick. Sometimes that will happen. But here we can't apply the same trick because the sibling of 10, 22, is black. So over here, the good thing was that the sibling of 11 was also red. And so everything was sort of symmetric in this picture. Here it's not symmetric. We have to do something different. And this is actually where we switch into the phase where we do rotations and not recolorings. Well, and recolorings, but not just a color. Okay, so we have a problem here, and I'm going to rotate 18 to bring 10 up. That's my next step. So this should be, this is just an application of that picture. Okay, in the right direction. So now at the top we'll have 10 because we're bringing 18 is going to fall down here, 10 is going to come up. Okay, and then we have to redistribute the subtrees. So 8 will go over here. Over here we have 18. And the left subtree of 18 will be the 11 node. Good. And all of its subtree. And the right child of 18 is the same as it was before. Okay, and the colors, so far I'm not going to change. I think that should work. Okay, why does this work if I don't change the colors? This is red. Okay, how come the black heights are still okay here? What's the general principle? What's going on? I'm only affecting a couple of nodes, really. Okay, in this picture, the subtrees alpha and beta and gamma, they stay the same. Yeah? It's 22 red. Good question. 22 should be black, sorry. Yeah, I just was copying from there. So I'm only really changing A and B. You know, these subtrees what's their black height going to be? Well, let's look at the picture. I have a subtree here. This is alpha. This is beta. This is gamma. Okay, and this is A, and this is B. The black height of this tree is... This is another easy question. Sorry? 1, right. Black. And this one? 1. This one, or sorry, this one is 2. Better not be. So when I say black height of a tree, I mean the black height of its root. Okay, that means you don't count the root. So this is also 1. This one is also 1. Okay, these are actually valid red-black trees, right? Their root is black, and they have a nice black height. So that's cool. And not only are they red-black trees, but they all have the same black height. So you have an idea?
Is there an inconsistency in the notation? Because you write routine 18, but
Oops. Good point. This is inconsistent.
should be 10.
I don't know. I checked the text. I think it should be 18. I think that's wrong. So I should be consistent one way or the other. Thank you. Yes. All right. So you can vote. Which one would you prefer is correct? This or that one? I think, should I stay consistent with the text? That's probably easiest. It doesn't matter, right? It's just whether I'm highlighting the top node that I'm playing with or the bottom node. So, sorry. I'm going to switch. You'll find that the rest of the notes are actually consistent with the text online. So I'm going to change this one. Sorry about changing old stuff. But this I'm going to make B, and this will make A. Let me double check that's what I have written down here. Yeah. I also had the wrong thing written and then crossed it out. OK. Thank you for pointing that out. Okay, again, it's just a notational thing. It doesn't really matter which way we go. But that's what the text does. So any ideas why? I have these nice trees. So now why aren't I playing around with black heights? Why are they all staying the same? Why is this a good thing for me to be doing? Okay, if you want to give a one-word answer, the one-word answer is either red or black. So let's see who can guess the right one. Anyone want to guess a color? Flip a coin. Red? Red. Good. Right answer. Red is the answer because these two nodes are both red. Right? And I'm only moving around red nodes. So sure, all the black heights stay the same. Okay, that's what's going on here. Because these two are red, which is the problem situation, that means I can flip these nodes around. It doesn't matter which one's above which one, because all of the paths will go through the same number of black nodes if I don't mess around with these subtrees. That's what